Hello, students. So here is an example of a spinning object. This is a top that I've made out of a mass and an electrical plug. And it just sits in there, and I'm just going to spin it. And it spins around. And the point of this is that it spins in the direction that this little arrow is pointing. Right? Because that's basically the way I can spin it. I can't quite make it go the other way smoothly. Maybe that will work. So if I needed to go that way, I can do that. So let's take it apart for a second. What's going to happen here is I want to make this thing rotate like this. And from your perspective, we would call that clockwise, right? Because you have your clock 12, 3, 6, 9, and we'd be making it rotate that way. Right? From your perspective, it looks like that. But what does someone on the back of it see? Right, if I flip it over, right, let's put the this thing in. So it's spinning like this. And let me put this marker back on it so you can see it. Right. So there's an obvious mark on it, and we're going to put one just on the other side, just the same way. Right, so they both have a mark on it. And so we're going to spin it. And so you can see that if I hold it here with the light on it, that's the way we're spinning it. Right? Now we're going to flip it over, still spinning it the same way. Right? My hand is still trying to do the same sort of thing. And what you see is it goes in the other direction. Right? This is kind of a hard thing to film, but it matters which side of the spinning object you're on, whether it's clockwise or counterclockwise. So if we wanted to find a vector that described the rotation of the spinning object, that would be a problem. We'd have to come up with something. And what we came up with is right-hand rule number 1. So what we're trying to talk about is we have this object. That looks horrible. Let's try that again. I have this object that's spinning around like this, and this is the direction it's spinning, but we want to define a direction for the angular velocity. Which is this omega. Now, you guys that are doing the optional, the kinematics, rotational kinematics activity, we talked about that in there. But for those of you that haven't, this video hopefully explains a bit about it. So the idea is that when we have an object that's rotating, let your fingers curl in the direction of the rotation. So fingers curl in the direction of the rotation. Your thumb is your angular velocity. So in this case, we're spinning like this. In order for my fingers to curl in that direction, my thumb has to go into the page. So for this, omega here is into the page. Now, when we spin this back the other way, like that, so something spinning around like this, omega is going to be out of the page. Hand wraps around the direction it spins. My thumb points in the direction of the velocity. All right. So what you're doing is you're grabbing the rotation axis. You can see the little piece of metal that is rotating. When I spin it like that, I would grab it like that. When I spin it like this, so it's rotating clockwise from the camera perspective, I'd grab it like this. My thumb would point downwards. I don't know why I have to have a crooked thumb, but you know, that's just what it is. So this is right hand rule number 1. Right hand rule number 2 has to do with different vectors. And we talked about this in the previous video. Here are 2 vectors, A and B. So in this case, we could associate 2 different vectors here, right? Right. Remember our definition for the tangential velocity is r omega. So omega is defined so that this is going to make sense. For this red circle, our tangential velocity is that way, and our radius is from the center of the circle out. Right. So our omega here is going to be defined, right? Now we can apply right hand rule number 2. All right, we're going to make omega our first. So what we do with right hand number 2, fingers start first finger in the direction of the first vector, second finger in the direction of the second vector, thumb to give you the third vector. So here, to make this make sense, our first vector, so omega, is into the page, so point down. Our second one is r, is now currently that way, is toward me, and then the tangential velocity is across the page like that. And that makes sense if we rotate anywhere along the circle, that needs to make sense, right? So if we're over here, this is our vector r, and this is our vector. So this tangential velocity is really omega cross r. And it's always written so that omega is at right angles to r. Isn't that fun? Now, this also works the other way, is our tangential acceleration is alpha cross r. And for that matter, we can probably write a little bit of displacement vector, which is going to be tangent to our circle, is going to be some sort of angle vector cross r. Just so you're fully aware of that. All right, so that's a good stopping point for right-hand rules. What I'm going to recommend is when we start using right-hand rules in seriousness, one, just have a one constant pattern, right? I always do point along the first vector and make the bird to the second vector, and then your thumb is the third one. But other textbooks may swap that around. I've also seen in one textbook is all your fingers go in one vector and you push in the direction of the second vector. And that causes your thumb to go in the direction of the third. So Find one sensible right-hand rule, remember it, and stick to it. And I'm always going to do point to the first vector and finger to the second vector and thumb is the third. I'm always going to do that. This is the physics gang sign. Congratulations, you're in the group.